Hello, my name's Clinton and I'll be your guide through this module of Day 4. We're going to talk some more about mathematical induction, focusing mainly on examples. Please don't forget to pause this presentation at any time if you need a bit more time to think about something. We're going to take a look now at some more examples of mathematical induction in action. The statement here that we need to prove is that if we take some number r which is not 1, and then add up the first n powers of r, starting with r to the 0, which is 1, so that is if we add up 1 plus r squared plus ... plus r to the n, we get 1 minus r to the n plus 1 over 1 minus r. You might have seen this geometric series formula in high school when calculating compound interest. Remember, the first step in mathematical induction is proving the base case, that is, showing that the statement is true for n equals 1. When n equals 1, we're adding up r to the 0 and r to the 1, which is 1 plus r. The right-hand side when n is 1 is 1 minus r squared divided by 1 minus r. Since 1 minus r squared is a difference of two squares, it factorizes as 1 minus r times 1 plus r, so this cancels to 1 plus r. And so the claim is true for n is 1. Now we need to go ahead with step 2. We assume the statement is true for n and show that it follows for n plus 1. The assumed data, that is the statement for n, is written down here. And here's what we have to prove using this assumed data, that the sum of the first n plus 1 powers of r, again starting with r to the 0, which is 1, is equal to 1 minus r to the n plus 2 over 1 minus r, since n plus 1 is n plus 2. The left-hand side of what we want is written here, and if we group it like this, we can rewrite all these terms like so, using the assumed data. Now put everything over the common denominator 1 minus r, expand the top, and notice that the r to the n plus 1's cancel. This is exactly what we wanted, and so we're done. Another example now. Let's show that for any n greater than or equal to 1, 5 to the n plus 3 is divisible by 4. Again, for our first step, we need to show that the statement is true for n equals 1. But 5 to the 1 plus 3 is 5 plus 3 is 8, which is 2 times 4, so the statement is certainly true for n equals 1. For step 2, for our assumed data, let's suppose 5n plus 3 is divisible by 4. Say it's equal to 4 times k for some number k. Then we need to somehow use this to show that 5 to the n plus 1 plus 3 is also divisible by 4. We need some way now of connecting the dots and exploiting our assumed data. We're going to have to use a bit of a trick here, and rewrite 5 to the n plus 1 plus 3 as follows. We'll rewrite it as 5 times 5 to the n plus 3, using the index laws. Now, inside this bracket, let's add and subtract 3, which of course has no effect. Because now we can use the assumed data to replace 5 to the n plus 3 by 4 times k, since we've assumed that this is divisible by 4. Expanding everything out now, we have 20k minus 15 plus 3, which is 20k minus 12, which is divisible by 4. In fact, it's 4 times 5k minus 3. So now we're done, because the statement for n plus 1 follows from the statement for n. Let's finish up with one final example, an inequality which we're going to prove is true by induction. We want to show that 2 to the n is greater than or equal to n plus 1 for any positive integer n. Again, for step 1, we need to show that this is true for n equals 1, which is easy because 2 to the 1 is 2, and certainly 2 is 1 plus 1. If we write out the assumed data, we're assuming that 2 to the n is greater than or equal to n plus 1, and trying to use this to show that 2 to the n plus 1 is greater than or equal to n plus 2, which is n plus 1 plus 1. Again, we now need to come up with some way of connecting the dots and exploiting what we know. Now the left-hand side, 2 to the n plus 1, can be rewritten as 2 to the n plus 1 is 2 times 2 to the n, again using the index laws. And since 2 to the n is greater than or equal to n plus 1, by the assumed data, 2 times 2 to the n will be greater than 2 times n plus 1. And expanding this, we get 2n plus 2. Writing this out very explicitly, we see we have 2 n's and 2 1's, which is definitely bigger than if we just had one n and two 1's, since n is a positive number. And this is what we wanted on the right-hand side. So as usual, we can conclude that the statement is true by induction. Have a go at these practice questions to get a feel for how to do proofs by mathematical induction.